In this video, we're going to be talking about ratios, proportions, and the cross-product property. So how can you solve proportional statements? And just so you get an idea of where we're going with this, from this we're going to build and talk about similarity of geometric shapes. So first, let's get some vocabulary words out there. A ratio is a comparison of two numbers. The only rule is that you can't have zero. Okay, so your numbers can't be zero. There's 3 different ways to write a ratio. You can write it as A to B with this little colon. You can write it out in words, A to B, or you can write it as a fraction of A over B. Okay. We are usually going to be using the fraction version of ratios in what we're dealing with because they're just easiest to work with. So a proportion is just an equation that says two ratios are equal to each other. So basically it just means that when you compare two numbers, that comparison number is the same. So we could have the ratio of A to B and the ratio of C to D, and we could just say those are equal to each other. That's a proportion or proportional statement. Now the cross product property is sometimes called cross multiplying. And what it does for us is it allows us a way to solve proportions. So if we have this proportional statement, A over B equals C over D, and so we want to get rid of the fractions so that we can deal with the with just the numbers. What we can do is we can do what's called cross multiplying. And what you do is you multiply the top of one fraction with the bottom of the other. So we get AD, and then you multiply the top of the other fraction with the bottom of the other. So AD equals BC. And it doesn't matter if you write it as AD or DA or BC or CB, as long as you get the A and the D on the same side of the equation and the B and the C on the same side of the equation. So let's take a look at how we would use this cross product property in order to solve some proportions. So say I want to solve for x in this first example, in example A. What I'm going to do is I am going to cross multiply. So I'm going to get 15 times the x, so 15x is equal to 9 times 10. So 15x is equal to 90. Then I'll just divide both sides by 15. 90 divided by 15 is 6, which means that x is equal to 6. And that would be the solution to that proportion. Okay. So let me do one more example with you guys. In example B, we're doing the same thing. Our variable this time is on the top, but that doesn't make a difference. We're still going to set it up the same way. 7 times 4 is equal to 10 times A. So 28 is equal to 10A. We'll divide both sides by 10. So we have 28 over 10. You can either leave that as a fraction, or you can get a decimal for me. 2.8 is equal to A. And that would be the solution to that proportion. I'll let you guys work through C and D on your own. I want to jump down to this next row where things are a little more complicated. Okay, so let's look at example E. 2 over x minus 1 is equal to 4 over 8. So what I'm going to do is I'm going to cross multiply. But I'm going to do one thing before I actually multiply. I'm going to put this x minus 1 in parentheses. And I'll show you why that's important. So I'm going to get 2 times 8 is equal to 4 times x minus 1. And I need to have those parentheses there because I need to multiply this 4 to the x and to the 1. So that right side of the equation will turn into 4x minus 4. And the name for that is distributing. So I'm distributing the 4 into the parentheses. And 2 times 8 is 16. Then I'm going to go ahead and add 4 to both sides. So I get 20 equals 4x. And I'm trying to get the x by itself. So 20 divided by 4 is 5. So my final answer is x equals 5. Okay. I'm going to let you do F on your own. G, we're going to do the same way. I just want to work through a couple more examples. Remember that whenever you have these expressions, instead of just a variable, you're going to put parentheses around them before you cross multiply. Then you'll get 8 times 3 is equal to 5 times 2x plus 5. Okay. Then you're going to want to distribute this 5 in. So you'll get 10x plus 25 is equal to 24. Subtract 25 from both sides. So you get -1 equals 10x. Then to get rid of that 10 that's in front of the x, you're just going to divide both sides by 10. So x is equal to -1/10. And I'm going to leave this one as a fraction. Okay, so that's what my x would be in this situation. Okay. Let's go ahead and talk through some solving proportions using word problems. So the cool thing about proportions is that they actually come up quite a bit in the real world. So for example, in example A, we have a question about the exchange rates between different types of money. So the money used in Western Samoa is called the tala. The exchange rate is 17 tala to $6. How many dollars would you receive if you exchanged 51 tala? So what we're going to do is we first have to set up the proportions. So I'm going to use this piece of information first. 17 tala to $6. So that is one ratio. I'm going to put 17t, so that I know that's the tala, over $6. So that's my first ratio. That's important. The next ratio that I'm going to set it equal to is I have 51 tala over some amount of dollars. I'm going to just put an X there because I don't know how many dollars I need. An important part of my setup is that these t's both need to be on the top. Okay, like your talas need to be on the top and the dollars need to be on the bottom. Or you could have the dollars on the top and the talas on the bottom. But you just need to be consistent. Once you have this set up, we're just going to cross multiply. So I get 17x equals 6 times 51. Whoops, 6 times 51 is equal to 306. Divide both sides by 17. You get 18. So x equals 18. So that means that when I trade in 51 tala, I'm going to get $18 back. Okay. So I'm going to show you another way to work through this same exact problem by setting up a different kind of ratio and proportion. So in this first example, I set up the ratio of talas to dollars. Okay. I'm going to set up a new proportion, and it's going to be the amount of money in the original exchange rate, so 17 tala, to the amount of money that I am giving, so 51 tala, and that's going to be equal to the amount of dollars in the exchange rate over the amount of dollars that I am giving. So in this case, again, you've got this important relationship where the talas are part of the same fraction. And another important part of this fraction, of this proportion, is that the top, that's my exchange rate. It's the 17 tala to $6. So I've got to make sure that those two things stay the same. They either got to be part of the same fraction, like in the first example, or they both need to be the numerators of the fraction. So I'm going to go ahead and cross multiply. I'll get 17x is equal to 306, which you'll notice is the exact same equation that I got previously. So this is going to give me the exact same answer. It's just a little bit of a different way of thinking about it. Okay. So let's just kind of make sure we understand the difference between the two. In the example on the left, in the blue ratios, each ratio is number of tala to number of dollars. And you've kind of got a fraction for the exchange rate and then a fraction for the amount of money you are exchanging. In the second example, with the black example on the right, I have a tala fraction equal to the dollar fraction. And the numerators of both fractions are the exchange rates, 17 tala to $6, and the denominators are the amount of money that you are exchanging. So let's work through some other examples of word problems. So in example B, we have a really interesting example, which is about scale factors. So a model satellite has a scale of 3 centimeters to 2 meters. That means that for every 3 centimeters in the model, it represents 2 full meters in the actual satellite. And we use this kind of idea a lot, like on maps. We'll say 1 centimeter is equal to 1 mile, and then we'll use that proportion of that scale factor to figure out a certain distance. So if that's our scale factor, if the model satellite is 24 centimeters wide, how wide is the real satellite? So let's start by just setting up a proportion. And again, there's 2 different ways to do this. So go ahead and do whichever way makes the most sense to you, and you should get the exact same answer. So the scale factor is 3 centimeters to 2 meters. And I want that to be equal to my other ratio, which is the width of the satellite. So it's 24 centimeters on the model, and I want to know how many meters it is in real life. Okay. So one way to think about this, maybe it'll help if we label this. This proportion here, that's the scale factor. And then this is the width of the satellite. Okay. Then it's important to also notice the relationship between the tops and the bottoms. So the bottoms of my fractions here, the 2 meters and the x, that's the actual. So I guess maybe I won't use the word actual, but that is the measurements of the satellite. And then this numerator, that's the dimensions of the model. Okay. So both the numerators of the fraction and the denominators of the fraction and the fractions themselves, they have to have this relationship between them. Okay. So I'm going to go ahead and rewrite my proportion out over here. It's kind of messy over there since I drew all that stuff in. And we're going to use this to solve. So I'm going to get 3x is equal to 48. I'll divide both sides by 3 to get x equals 16. And that would be 16 meters, because that's how wide the satellite is in real life. Another way to set up this same problem would be to set up a fraction with both your centimeter measurements. So here's your ratio of centimeters, 3 centimeters to 24 centimeters. And that should be equal to your meter measurements. So 2 meters to how many meters? You'll cross multiply, end up with the same equation, and of course with the same answer. All right, let's go through this next one together. If you want to press pause and try it on your own, I'd recommend it, and then come back and work through it together. A baby giraffe standing near a flagpole casts a shadow that is 25.5 feet long. If the 17.4 foot tall flagpole casts a shadow that is 76.6 feet long, how tall is the baby giraffe? Okay, so we have 2 different measurements here that we're looking at. We're looking at height of, like, vertical height, and we're looking at shadow length. Okay, so let's think about creating a ratio that represents the flagpole. So let's say it's 17.4 feet. So that's 17.4 feet tall. So that's its vertical height. And that is related to the 76.6 foot shadow. Okay, so that's that fraction is like, that's the flagpole. That's the dimensions of the flagpole. Okay, so now I need to create the same fraction with the dimensions of the giraffe. Okay, so the baby giraffe standing near a flagpole casts the shadow that is 25.5 feet long. So this is the shadow length. So I'm going to put it on the bottom of the fraction because that's where I'm putting my shadow lengths. And then the numerator will tell me how tall the giraffe is. Then I can go ahead and cross multiply. When I cross multiply, I'm going to kind of ignore the units that I wrote down just for simplicity's sake. So I'm going to have 17.4 times 25.5 is equal to 76.6x. This left side will turn into 443.7. So 443.7 equals 76.6x. I'm going to divide both the sides by the 76.6. And that is going to tell me how tall this giraffe is. So this giraffe is 5.8 feet tall. Okay. And there is another proportion you could have set up for this one. So if you set up the alternative one, that's okay, as long as you ended up with the same height for the baby giraffe.